Now we want to go further on with the exponential growth and decay. So we want to explore a different type of formula, one that's probably a bit more useful and has a lot more application than the one we saw in the 2-unit course. And remember, the one we saw in the 2-unit course, we had the idea that with exponential growth and decay, we get a situation where the rate of change of the function itself is proportional to the actual population of that function. So if we're talking about population, or it's whatever the function it was, the exponential function was, the rate of change was proportional to that. And that's what we had. That we had that classic situation. Ka to the kt, or where y is equal to a to the kt, it was proportional to what we started off with. And that was the nature of an exponential function. Now, what we do this time with the extension one, we consider that we have a different starting point as such, where we have a constant being added. So p plus ae to the kt would be equal to some value n. So you can see it's a little bit different. We've just had adding a constant. So the difference there is that the rate of change starts to be the ndt outside of k times n minus p. So again, it's proportional to the difference here between the n and the p. That's what we're actually going to get. How do we prove this function? Well, if we had n is equal to p plus a e to the kt, dn dt would be k times a e to the kt, because p is a constant. If we consider that a e to the kt, though, by manipulating this function, would be n minus p, then we can substitute a e to the kt as n minus p. So there's our proof. A lot of times you're asked, that's the first part you're asked to do in a question, is to show that that's true. We're quite happy to do it this way rather than do a differential equation and try and work with this equation and work backwards. We're not quite into that at the moment. You'll do those sorts of things at university, but we're quite happy for you to do it this way now. So because that's what we actually get as what we call a differential equation there. So let's have a look at applying this into a question. So we've got a growth rate of a population of birds is given us by dp dt equals k p minus 3000. So show that p equals 3000 plus a to the kt is the solution of the above equation. Well, if we start with p there, differentiate it, we get k times a e to the kt, which the 3000 differentiates to 0. a e to the kt can be written as p minus 3000, and so we can do our substitution there quite easily. So there's the first part done. In the next part, we want to show that if the bird population is initially 15,390 and after 2 years it's 17,420, find the values of a and k. Well, that's always going to be our trick, is to get a and k like we did in the 2-unit. So t is equal to 0. There's our population. So we're able to get a would be 12,390 because we subbed in the 0, and that starts to make it easy to get a. And t is equal to 2. P would be equal to 17,420. So we do that substitution. The only thing we don't know is k. So we start to clean it up. We subtract the 3,000, then divide by the 12,390 to get e to the power of 2k by itself. Now it becomes a log function. We can take our logs. By the definition of logarithm, 2k is equal to a natural log of 1442 over 1239. And then divide by 2, so we get our half log of 1442 on 1239. So there's k. Again, leave k in that form. We're quite happy. Then we want to find the population after 10 years. So after 10 years, we get our population. There's our value of e. So t is equal to 10, and that's the expression for the population, which will come out to approximately 29,457. And then the last part, we wanted to find out, well, how long does it take for us to get to 1 million? So again, substitute p is equal to 1 million. We know what k is, and we want to find t. So I haven't written k out all the time. I just kept k going through until we get down to the last part. So we can just subtract our 3,000, divide by the 12,390. So e to the kt would give us that expression. Kt then would be natural log of 99,700 over 1239, because we've divided by 10 there. And then we divide it by k, and k was the half of 1442 over 1239. Again, do that calculation. That'll approximately give us 57.84 years. So you can see how the questions don't change too much from what we did in the 2 unit. It's just we're dealing with an extra constant there, which just makes sure we need to change the problem around. We need to consider the problem a little bit differently. This time we've got a piece of metal, and it's heated to 95 degrees, placed in a room with a constant air temperature of 25 degrees. So logic would tell us that it would start to cool. It's a piece of metal that is in an area that is cooler than that, so you expect it to cool. And you expect it to keep cooling till it got to that air temperature. That would make sense. So eventually it would do that. So the idea is that when we have that situation, that it's an exponential function, and it would as t would approach infinity, when we get minus kt, well, e to the kt would approach 0. So a to the kt would approach 0, so it would all approach 25. So that's where we start to be able to say, well, that's our function we get for this problem. So 25 plus a to the minus kt. So, but what we want to do is find a and k. So here's the part A is going to give us that data, because initially t is equal to 0, so the temperature is 95. So a then would give us 70, because a to the kt becomes 1 when t is equal to 0. So a must be 70, because the 95 minus 25 gives us 70. And then we're told that after 5 minutes it's at 90 degrees. So 25 plus the 70, we get e to the power of minus 5, k times 5, so we're able to put our 5 in there. And then we're able to get to subtract 25 from the 90, and we get 65. We get a being 70, so we divide by that. We've got e to the minus k, 5k then is equal to that expression. It becomes a logarithm, because minus 5k equals natural log of 65 on 70, and then divide by the minus 5. Now notice we've got divide by minus 5, or multiply by minus 1/5. So minus 1/5 the natural log of 65 on 70, which then I've written as the 1/5. So I've changed the minus to a positive, but the natural log of 14 on what would be 13 on 14 becomes 14 on 13, because that would have been a negative as well. So 65 on natural log of 65 on 70 was a negative, so change it to 14 on 13. So doing the division, but change it round and becomes a positive, because we had the negative out there. So we had a negative times a negative, made it positive. When will the temperature reach 30 degrees? Well, T reaches 30 degrees. Oh, sorry, we finished the first part off. Temperature be after 15 minutes. We substitute in t is equal to 15. And we've got our k value from back here. We've substituted that in, and that would approximately be 81 degrees after 15 minutes. And then the last part, when t is equal to 30, then we're going to solve for t. So again, we're going to get a log function. We take it, subtract by 25, divide by 70, get e to the minus kt, and minus kt would equal natural log of 1 on 14. And we get the minus 1 on k. We had our value of k before, times the natural log of 1 on 15. And it would approach that temperature after approximately 178.05 minutes. So there's the way we start to attack these problems with exponential growth and decay. Similar to what we did in the 2 unit, we've just got that constant in there to change it around a little bit. So be wary of that and follow that form. But again, the questions are going to be pretty standard. They don't change very much from finding the values of a and k and then being able to either find the population or the time after at a particular point.